From the University of Arizona Distance Learning Program, this is Optical Sciences 505, Diffraction and Interferometry, with Dr. James Wyant. This broadcast is authorized by the Arizona Board of Regents on behalf of the University of Arizona. Any reproduction or retransmission of this course or use of same for granting of credit without the express written consent of the University of Arizona is strictly prohibited.
Well, I'll say good morning to everyone. So I got an email, I think it was yesterday, from Neil up in Boulder, Colorado. And Neil had been looking over the homework problems, and not just the problems that are assigned, he was looking over some of the other problems. And he noted that in problem number 2, WP-2, there were some things missing. And so if we can, maybe if I can zoom in right here. Can we zoom in on this? Okay. And what was missing are all these not equal signs. And I think I'm going to blame word 97 for that, because it was in last year's copy of the notes, but somehow in going from word 95 to word 97, these not equal signs disappeared. So I was okay, theta is equal to 0 and rho naught's equal to 1. And the second one here, theta is equal to 0, rho naught's not equal to 1. And the third one, theta is not equal to 0, rho naught's equal to 1. And in the last one here, both theta and rho naught were not equal to 0. So those of you who are working additional problems, fill in the not equal signs, and it'll make it much easier to work this, I think. So let's say thanks to Neil up in Colorado. Okay. Last class we were talking about polarization, and we're talking about circular polarization, linear polarization, and so now we're up to where we can talk about elliptical polarization. And so this is section, maybe we need to zoom, okay, 3.6.1.4, and just called elliptical polarization. And we're going to have two cases here. For the first case, which will be the simpler of the two, case 1, we will have that a sub x is not equal to a sub y. Remember, that was the difference between circular and elliptical. And we're going to have here that phi is equal to plus or minus pi over 2. So the phase difference between the two is plus or minus pi over 2. And so we can write here that for the two components of the electric field, E sub x is a sub x cosine kz minus omega t. And for E sub y, well, it'll be minus or plus depending on the sign of phi here, a sub y sine kz minus omega t. So same as we had for circular, except the a's here are not equal. And then it follows very easily that E sub x squared over a sub x squared plus E sub y squared over a sub y squared is equal to 1. And of course this is the equation of an ellipse. And so if we were to make a plot here of the electric field as a function of time or distance, and this would be the x and the y directions. So the electric field here would go around in an ellipse. And the nice thing here about the phi being plus or minus pi over 2 is that the ellipse is lined up with our axes here. And so this will either go around this way for left-handed circular, or it would go around this way for right-handed circular with time. That is. Okay, so that's kind of neat, the way this electric field goes around and maps out the ellipse here. Now, this was, it's kind of a special case. It was a case where phi was equal to plus or minus pi over 2. But we can still have elliptical polarization when that's not true. And so let's look at that for a second. So we will call this case 2. And this is a more general case than what we had up above. And so now we have that phi is not equal to pi over 2, plus or minus pi over 2. And it's also not equal to plus or minus pi. That would be linear polarization if we had that. And so we just have here the E sub x is a sub x cosine kz minus omega t. And E sub y is a sub y cosine kz minus omega t plus whatever this phi is. And so I just like to write here that E is some component in the x direction plus some component in the y direction. Now we could play around with this equation a little bit, and I have the derivation here, but I don't think I'll go through it. I'm just going to write down that after, well, the interested student will show. And it's not too hard, but it'll show that E sub x over a sub x squared plus E sub y over a sub y squared minus 2 E sub x over a sub x E sub y over a sub y times the cosine of phi is equal to the sine square root of phi. And this is fairly straightforward to get to that. And so this is also the equation of an ellipse. But the thing about the ellipse is that it's no longer lined up with the x and y axes. And I'll show some plots of these in a little while, but right now I'll just sketch one. And so this is, I don't know, but this particular guy will make it lined up with this axis. And my drawing ability is not great. But as everyone can see, that's a great ellipse, right? Well. So anyway, this ellipse here will fall inside of a box here. That has a side of 2ax and a height of 2ay. And the angle here will depend upon these phi's and also the ratios of the a's. In fact, I'll give you the equation here. Not going to derive it, but we'll write it down. If this angle of the major axis with respect to the x-axis is alpha, it turns out that tangent of 2 alpha is equal to 2 a sub x, a sub y, cosine of phi, divided by a sub x squared minus a sub y squared. Okay, so we still, for this general case here, when phi is not equal to plus or minus pi over 2, not equal to pi, we still will get an ellipse here. It's just that it's rotated. Now what I would write here is, let's write the state of polarization here in complex notation. Kind of summarize what we've seen. And so we have the E is some E naught complex quantity, e to the I kz minus omega t. And if this E naught here is real, then we have linear polarization. If it's complex, we have, of course, elliptical. And if it has equal real and imaginary parts, if we have equal real and imaginary parts, then we have circular. So that's kind of a convenient, compact way of just writing the electric field and determining whether we have linear, elliptical, or circular. So any questions up to this point? Okay. So I have a question for you. Who do we play in basketball tonight? Oregon State, is that right? I actually wasn't sure myself. It's either Oregon or Oregon.
Yeah, Oregon State's on the weekend.
Oregon State's on the weekend, Oregon tonight. I don't know. I didn't know the answer. How many are going to the game? How many are truthfully going to the game? You believe them? How many are going to watch it on TV? Yeah. How many are going to be doing homework for 505 instead of watching it on TV? One liar in the back. Yeah. And unfortunately, I'll be in New York City tonight, so I'll miss it. Oh, well. Okay. Well, you know, I actually was going to bring them, but my son convinced me he could also give them away to someone. But for some of these games, I will. I'll bring them. We have a little pop quiz or something to decide who gets the tickets. Yeah. I have 2 tickets in the 9th row and 1 ticket in the 1st row. It's not bad. Okay, let's talk a little bit more here about polarized light. The first thing, I mean, we think of elliptically polarized light, and so far we've been kind of thinking of it as linear polarization. With different amplitudes and different phases, but we think of it in terms of 2 linear polarizations. But another way of thinking about it, thinking about elliptical polarized light, is to think of it in terms of a left-handed and a right-handed circular polarized beam. So let's see if we can figure out how that works here. So elliptically polarized. Light can be thought of as a superposition, of 2, well, let's say of right and left-handed circularly polarized beams. And it's fairly simple to show that, so let's do it here. So we could always, we'll pick our x and y axis such that we can say the following. So pick x and y axes such that E is E sub x in the x direction plus I E sub y in the y direction. So we'll just rotate our axes so the ellipse is lined up with the axes. We can write it like this. You might put a plus or minus here, but I'll just worry about the plus here. And so we could write that as E sub A plus E sub B in the x direction plus I times E sub A minus E sub B in the y direction. We can do that as long as, E sub x, we just say, well, E sub x is some number E sub A plus some number E sub B, and that E sub y is this number E sub A minus E sub B. Okay? And so we can write here then that E sub A is what, 1/2 E sub x plus E sub y. And we can write then that E sub B is 1/2 E sub x minus E sub y. And so we can rewrite this in that the electric field is E sub A times unit vector in the x direction plus I unit vector in the y direction plus E sub B times unit vector in the x direction minus I unit vector in the y direction. And so we have a left-handed circular and we have a right-handed circular. So it worked out. So the elliptical polarization can be thought of as a sum of a right-handed circular polarized beam and a left-handed circular polarized beam. Buy that? Kind of neat way of looking at it, I think. Okay, well that's everything we're going to say about elliptical for now anyway. So let's see, we had linear, well we had unpolarized light, we had linear, we had circular, we had elliptical. See, there was another one in the list, wasn't there? I forget. Oh, partially. Oh, okay, good. So that just happens to be section 3.6.1.5. And it's going to be a very short section, as you'll see. So this is partially polarized light. And so all we're saying here is that we have a mixture of a polarized beam and an unpolarized beam. So I'll write that down. Mixture of a beam in a pure polarized state and an unpolarized beam. Okay. That's it for section 3.6.1.5. Okay, so we're experts on the states of polarization. Now I want to have a very short section here on retarders, and then we'll go to Jones calculus and Stokes vectors, Mueller matrices, and that stuff. So this is section 3.6.2, just retarders. And first off, Retarders are going to change the state of polarization. And what we're going to do, this is going to be some little device, we'll send light through it, and one of the two, we can break up the electric field into an X component and a Y component, and one of these fields will see a larger optical thickness, and we'll get a phase delay between the two components of polarization. So I'll just write down here from my notes, one of the two orthogonal components caused to lag in phase behind the other component. Oh, by some predetermined amount. And so we can say that the phase, after the light passes through this retarder, there's a phase difference between the two components that goes as 2 pi over the wavelength times the thickness of the component times the refractive index difference for the two directions of polarization. And so it's just 2 pi over lambda d times some delta n. And so this retarder is made out of some birefringent material such as mica or calcite or quartz, and we get this retardation between the two states of polarization. And if we look at 3 examples here real fast, if we say we have a wave plate, a one wave plate, which is not going to be a very exciting device, but now the phase difference between the two components after the light goes through this wave plate will be 2 pi. And so we have d times whatever the delta n is for this material is equal to the wavelength. Not very exciting, maybe. Gets more exciting if we go to something like a half wave plate, where now delta phi is pi, and that d times delta n is a half wave. And this will do interesting things to the state of polarization. And we have a thing called a quarter wave plate. Delta phi is now pi over 2, and so d delta n is a quarter wave. So if we have an optical system and we put these retarders in this optical system, we're going to change the state of polarization. And you can always just break the initial polarization into two components and introduce this phase change between the two, and calculate how it changes the state of polarization. And maybe I'll look at an example here. Let's say we have a quarter wave plate. And we send light through it. So these are the axes of our quarter wave plate. And let's say the initial polarization, I use the red light here. Our initial polarization is, well, let's make it at 45 degrees here. Initial polarization at 45 degrees. And so we could break this polarization up into two components along the x along the y. And if this is a quarter wave plate, then we said the light going through the two axes here will change. There will be a difference in phase of 90 degrees. So if this initially is at 45 degrees, linear polarization, can you say what the state of polarization will be that comes out of the quarter wave plate? It's going to be circular, right? Because we have introduced a 90-degree phase difference between the x and y components. So it will be circular. What if this is not 45 degrees? Let's say it's 32.5 degrees or something. Be elliptical, right? Okay. So that would be elliptical. Let's say let's look at one more example here. Let's look at a half wave plate. This is half wave. And let's say the initial state of polarization here is like so. And so we can break that up into two components, here and here. And let's say this angle here, I didn't leave enough room, but let's say the angle is theta, right here. Half wave plate. So we're going to introduce a 180 degree phase difference between light along this axis and light polarized along this axis. So what can you say about the light coming out of this half wave plate? Well, simple-minded thing is, it's 180 degrees. So this, when it's positive, let's say this goes down negative. And this would not change. So our resultant polarization here would come down here like so. So the state of polarization is still linear, but it's rotated at an angle of 2 theta. So the half-wave plate operating on linear polarization will rotate the angle of polarization by twice the angle between the axis and the initial state of polarization. Still linear, but rotated 2 theta. Well, we could go through here and we could calculate the effects of half-wave plates and quarter-wave plates and any fractional wave plate on any initial state of polarization if we wanted to. And it's fairly straightforward. But now if you have an optical system where you have a few wave plates in it at different angles and stuff, I think you can see that it soon becomes somewhat messy. And it's very easy to make a mistake. So there was this guy, R. Clark Jones, who came along from Toledo, Ohio. I mention that only because I'm more or less from Toledo, Ohio. R. Clark Jones came along and came up with this mathematical description here of polarization, and called the Jones calculus. So we'll first start out with a section of 3.6.3 and called mathematical description of polarization. And in this section here, we're going to talk about Jones calculus, which is 3.6.3.1. And Jones calculus is going to work with polarized light. Completely polarized light. And it will keep track of phases and as well as the state of polarization. It's very, very handy. And then there will be another section coming along later on Stokes vectors and Mueller matrices, and that will be for partially polarized light. Well, whenever I think of Jones calculus, I think of R. Clark Jones. And when I was a graduate student, I took a one-semester course in polarized light from a man by the name of Lem Hyde, who had worked with R. Clark Jones. R. Clark Jones spent his career working at Polaroid Corporation. And it's kind of interesting that, he says that everyone in optics, as you get older, you get a little crazier. Now, I, of course, don't think that's true, but anyway, he said that was true. But he said R. Clark Jones was the opposite. R. Clark Jones started out being crazy, and the older he got, the more sane he got. So I don't know. Anyway, I was on a few years later after taking that course, I just happened to be on an airplane with R. Clark Jones. And so I was watching this guy, if he had been crazy and was getting more sane with time, I wanted to see just, what was wrong with him. And he seemed like a very good guy. I liked him a lot. And I couldn't see anything strange at all with him. Anyway, we got off the plane and we got our bags. And the first thing he did was he got out his jackknife and he cut the little tag off of his suitcase, what the airlines had put on. And he just did that immediately. And I thought, maybe that's a little strange. But now I realize that when I travel and I check bags and I get my bag, you know what the very first thing is I do? I'm just compelled to do this for some reason. I have to get out my jackknife and I have to cut off that tag. I cannot resist it, so I don't know. Anyway, I'm warning you, maybe in the future you too will have that same problem. Anyway, it's not too serious of a problem. Anyway, Jones calculus is kind of simple and really very, very powerful. And all we're going to do is, it's neat, I love it. We're going to take polarization and do a matrix representation of it. So just say a matrix representation of polarization. So we can say the electric field here is some E naught x in the x direction plus an E naught y in the y direction. And so that's equal to E sub x, E sub I, theta sub x in the x direction plus a E sub y, e to the I, theta sub y in the y direction. And the way that Jones would write this is he would write using a Jones vector. And he would just say, E naught x, E naught y is E sub x, e to the I, theta x, E sub y, e to the I, theta y. Okay? So that's our Jones vector. Now, we normally work with Jones vectors that are normalized. And so let's kind of write that down for a minute here. So we will normalize. So we're going to divide by some complex number such that the sum of the squares of the absolute values of the two components is unity. So divide by complex, whatever it should be, some complex number. Such that the sum of the squares of absolute values of the two components is unity. I mean, we don't have to do that. Sometimes I do it, sometimes I don't do it. So if we had x polarization, 1, 0. So this is X polarization in linear. Okay. Linear in the X direction. We just write that as 1, 0. That's our Jones vector. Y, oh, this is a tough one here. It'll be 0, 1. Okay. Now let's say, I'll have you help me. I'm getting lost here. Let's say we're polarized, linear polarization. At 45 degrees. What would my Jones vector be? Need help. So, linear polarization, 45 degrees. Anyone can help me? All right, 1, 1, good. And if we want to normalize it, square root of 2, 1 over square root of 2. You know, sometimes you do this, sometimes you normalize, sometimes you don't. Okay, good. Let's go circular. Need help. What would it be here? 1, what? Right, or I, I'll say. And I don't know if it's right-handed or left-handed, so I'll put plus or minus I. And if I want to normalize it, 1 over square root of 2. Okay, so that's not too hard. And if you go to Heck's book, you can find a list of them. Or if you go to the handouts I gave you today, if you're watching live on TV, maybe you have a problem. But the handouts are in the mail. How's that? They're also up on the website if you want. But, I just went through here, and I actually I typed them out here in Mathematica. Anybody use Mathematica? Yeah. I love Mathematica. I mean, here I was able, it's a convenient, fairly easy way to write equations. Plus, once you write the equation, I mean, you can write equations in Word too, but if you write your equations in Mathematica, after you write them, you can actually do something with them other than look at them. So anyway, you have a handout here just saying linear polarization is 1, 0, and that's the linear horizontal, linear vertical 0, 1, and we have linear plus 45 degrees, and linear minus 45 degrees, and right-handed circular. Mathematica likes capital I as opposed to little I, so this capital I here is square root of minus 1. So that's right-handed circular, and if we go here to the next page, we have left-handed circular, right elliptical, left elliptical, and so on. So anyway, we can write the state of polarization then pretty nicely in these little Jones vectors. Now the next thing is we want to some way write what a polarizer does. And this is a little trickier. Fortunately, it's not real tricky. I shouldn't say it tricky, but Jones has also written it all down for us. But we could also figure it out fairly easily. But I wrote down some here that say a horizontal linear polarizer. Turns out that there's a matrix with this that is going to go as, in this case, 1, 0, and 0, 0. And a vertical linear polarizer will turn out to be 0, 0, 0, 1. And we'll come back to this in a second. But let's see how we might use that then. So we'll come back to what these matrices are in a minute. Let's see how we might use them. So if we go back here, just to the vectors for a second. And let's say from the table we have there, whatever, we know that a right-handed circular goes as 1 and minus I. And a left-handed circular goes as 1 plus I. So if we add together a left-handed circular and a right-handed circular, what do we get? We get a 2 and a 0, or linear. Okay? I mean, we could have done this with the equations just as well, but it's nice that it drops out of the vectors. So that's just working with the vectors. Well, we started to look here at these other matrices that have to do with the retarders. And so what we can do here is that we have a, what I'll call a Jones matrix, A, B, C, D. Matrix of an optical element. And I said before that, a linear polarizer would be something that goes like 1, 0. A horizontal linear polarizer goes 1, 0, 0, 0. But in any case, in general, we will have some 2 by 2 matrix representing an optical element. And so if I initially have some state of polarization A and B, whatever that is, and that goes through my optical element, then I can just multiply whatever the matrix is for the optical element on this, and I will get some A prime, B prime, which will be the state of polarization of the light after it goes through the optical element. So again, we could do this without going through Jones calculus here, but this is such an orderly fashion, orderly way of doing it, it's easy to keep track of things. And so all we have to do is to multiply this matrix, once we know what the matrix of the element is, times this vector to get the new state of polarization. Now, where it really becomes useful is if we have a whole bunch of these optical elements in the optical system. And so now, what we will do, so we have a train of elements. Okay? And so we have some initial polarization, A, B. And it first goes through some optical element that we can represent as A1, B1, C1, D1. Then it goes through another optical element, which we will say is A2, B2, C2, D2. And then maybe there's a whole bunch of other ones here. And then the final one it goes to is A sub n, B sub n, C sub n, D sub n. Whatever these are, then this is just equal to A prime, B prime. Okay? So that, it's a nice orderly way of handling polarizing elements, or retarders, or whatever. Well, let's go back here. We started to look at the matrices. Let's look at a couple more, and then we'll work an example or two here. And you'll get a chance with your homework to work another example, I guess. So we said before, linear, turns out a horizontal linear polarizer goes 1, 0, 0, 0. And I think if you think about this for a while, you can kind of see that will make sense, because that will pass the x component and will not pass any of the y component. While the vertical one here will not pass any of the x component, but will pass the y component. So that would be the matrix with a vertical linear polarizer. And then we can go ahead here and look at a linear polarizer at 45 degrees. And that's 1, 1, 1, 1 times a half. And I think if you kind of follow through how that works on the Jones vector, it sort of makes sense. Linear polarizer at minus 45 degrees would be 1 half, 1 minus 1 minus 1, 1. And then we can put in quarter wave plates. Put in a quarter wave plate with a fast axis vertical. And so that's, well, again, Mathematica likes capital E for what you normally would see as little e. So e to the I pi over 4, 1, 0, 0 minus I. And so that would, this here will make it then symmetrical on the two. And it turned out the quarter wave plate with fast axis horizontal is e to the minus I pi over 4 times 1, 0, 0 I. And the handout show that, you know, retarder, just a retarder or retardation phi with a fast axis vertical, 1, 0, 0, e to the minus I phi, and then out in front e to the I phi over 2. So this is actually keeping track of the phase too. It's, you know, it's going to help you calculate the state of polarization, but it will keep track of the absolute phase as well. And then a retarder with a fast axis horizontal would be e to the minus I phi over 2, 1, 0, 0, e to the I phi. And let's just work one example here. And the example I have in the notes is that we have a quarter wave plate with fast axis vertical and incoming light at 45 degrees. So the initial light here, and I'm not going to worry about normalizing factors out in front for this example. Normal light, the incoming light at 45 degrees will be what? 1, 1, and we'll forget about the square root of 1 over, or the 1 over square root of 2 factor. And if I now go to a quarter wave plate with the fast axis vertical, well, you can look at your handout. Tell me what this is. Forget about the phase factor out in front for the time being. What is this? 1, 0, 0 minus I. And so we can multiply this out. And so this is a tough one here. 1 times 1 plus 0 times 1. So that's 1. And this will be what? 0 times 1 minus I times 1 minus I. And so what is this? It's circular. And it's actually right-handed, but it's circular. And I think, you know, maybe I should have asked you before going through here what we would get, but I think we'd already talked about that before. We put a quarter wave plate in, oriented at 45 degrees to the state of polarization, and we would get right circular out. And here, I mean, it worked. Just did it. Okay. And I mean, 2 by 2 matrices are not hard to multiply, especially when you do it on a computer, which is the only way I do it anymore. But even if you didn't have a computer, it wouldn't be too hard. And so it works very well.
What do you mean by fast axis?
Well, the index in this case is going to be smaller, and so the light will travel faster for that direction of polarization as opposed to the other direction of polarization. Well, I mean, this works pretty well, and the only problem maybe right here is that, you know, we have a general retarder, but for retardation, but everything we have here is at horizontal or vertical, or maybe something here at plus or minus 45 degrees. And if you have an optical system, you don't always have things at 0, 90, and 45 degrees. And so you have to some way work with these retarders or whatever at different angles. And that turns out, thanks to R. Clark Jones, is also fairly easy. And there's another handout that I hope everyone picked up here. And out in TV land, you'll be getting it shortly. But let's just think for a second that we have, we have an XY coordinate system. What happens if we rotate this coordinate system? So let's say I have something specified in XY, and I want to rotate it to a new coordinate system, X prime, Y prime. And so I could just do that, and I have, initially I have some vector E sub X and some vector here E sub Y. And then I can break these up into the components along the axes of the new coordinate system. And so if I go X prime coordinate system here, along this X prime axis, well, I would have this was E sub X. I'd have an E sub X cosine of theta, this angle. And from E sub Y, now I get a component in this direction of E sub Y sine of theta. So now in my new coordinate system, I could say that E sub X prime is E sub X cosine theta plus E sub Y sine theta. And likewise, for E sub Y, take this component here and break it up along this axis, and I get an amount that actually turns out to be minus E sub X sine of this angle here. And then from here, I'm going to get a component that goes as E sub Y cosine of that angle. So this would be the E sub Y component. And if we want to use Jones calculus, we want to express this in matrix form. So I could say E sub X prime is, we write here that we have this rotation matrix, which will go as cosine theta, sine theta, minus sine theta, cosine theta. And so I would have E sub X prime and E sub Y prime given by this rotation matrix times E sub X, E sub Y. So this is a way of taking my data and expressing it in a different a rotated coordinate system. Any questions here? Okay. So if I go back to my Jones calculus, and look at my handout here, I just define this rotation matrix here, cosine, sine, minus sine, cosine. But now if we think for a second, how do we really use this? And this maybe becomes a little bit trickier. So I have the matrix for some component here, say horizontal direction. I have the matrix for that. So and now I want to use this guy at some other angle. So what I'm going to do is I'm going to, maybe I'll look down here first. I have some state of polarization. What I'm first going to do is to rotate that state of polarization to align up with my matrix, to line up with my retarder or whatever. So I multiply by here to line that up. Then I operate on that by my retarder, and I have the result, but I have the result in this rotated coordinate system. So what do I have to do? I have to rotate backwards here by theta to get it back into my initial coordinate system. So I actually have to operate this with my rotation matrix and then minus the rotation matrix in the minus direction to get everything back to my original coordinate system. So I'll take a sip of water while you think about that for a second. But now this turns out to be, that's very powerful, because I only need this little, few little definitions here for 0 degrees, and, well, actually I only need them for one angle, 0 degrees, and then I can calculate them for any angle that I want. And right down here at the bottom, I could do this by multiplying it out, but I'm lazy, so I used Mathematica. To calculate the matrix of a retarder or retardation phi having a fast axis at an angle theta from the horizontal. So I simply took the matrix we had for this retarder horizontal, and I sandwiched it between the rotation matrix and then rotation matrix in the minus direction, and did some magic thing in mathematical called full simplify, which did all the algebra for me. And instantly I got this, still a little bit of a mess. But anyway, this would be my 2 by 2 matrix for this retarder of retardation phi oriented at an angle theta from the horizontal axis. Okay. So you see how that kind of works out? Okay, any questions? Feel like you're an expert now on Jones calculus? And, well, after your homework assignment you will be. How's that? I mean, it's, I know, I like it. It's just, there's nothing magic there or anything, nothing really that complicated, but it's just such a nice, orderly fashion way of handling polarized light. It's the way you would think, a guy who immediately cuts his little tag off his suitcase. It's the way that guy would think about polarized light, I think. I don't know. Anyway, we could work some examples here. Maybe I'll work one example or so, and but I'll just do one maybe here. We're going to convert light transmitted vertical to transmitted at 45 degrees. And so if we have something that's transmitted vertical here, if we go back and look, that would be a 0, 0, 0, 1. And now I'm going to rotate this minus 45 degrees. So my rotation matrix here will become 1. Go back here, look at the sines and cosines and so on. It's going to be 1. Or maybe I should ask you, if I'm rotating minus 45 degrees, what is this going to become? First guy here is a cosine, and so there's a square root of 2 stuff out in front here, but it's going to be cosine sine minus sine cosine. So I could write that as a 1, a minus 1, a plus 1, and a 1. And then I have to rotate in the opposite direction, and so the cosines will stay the same sign, and the sines will change sign. And then I guess there's a 1/2 out in front if I kept everything. If we multiply this out, oh, terrible having to do this without my computer here. I don't have to do it without my computer. I have students here. You can do it for me. Better than my computer. So if I multiply these two, what do I get? Help? Well, I get a 0. Going to get a 0. Going to get a 1. Going to get a 1. And then I still have this 1, 1, minus 1, 1, 1/2. So I multiply this out, and I'll take care of the 1/2, okay? You can help me with the rest. What does that become? 1, 1, 1, 1. So we got the result here that we've gone from the transmitted vertical to the transmitted at 45 degrees. And let's see, I think if I go back here and find the right page, oops, I can't find the right page. Yeah, let's see here. Seem to have lost that page. Well, I have another I have another copy of it. I don't see the one that I used a minute ago, though. Anyway, another copy I had here was that this would be 1/2, 1/2, 1/2, 1/2, linear at 45, and that is indeed what we got here. So it works out pretty well. Anyway, we could spend all day doing examples here, but I think you get the idea. And you have one homework problem on this that will give you another chance to use it. So any questions on Jones calculus? Well, the next thing then, Jones calculus works very well for polarized light. It works well for coherent light. It keeps track of the phase. It's very useful in interferometry, and because it does keep track of the phase. Sometimes, though, we work with partially polarized light, and it'd be nice to have a way of handling partially polarized light. So that takes us to section 3.6.3.2. And this is going to be called Stokes parameters and Mueller matrices. And so this is going to be for partially polarized light. And we'll be able to calculate what we'll call the state of the degree of polarization. We will not be able to keep track of phase. So it does not handle phase. So for my career anyway, I've found this much less useful than Jones calculus, but that's just true for me. For other people, sometimes this is more useful than the Jones calculus. So what we're going to do here is that we're going to use 4 filters. And then we're going to define these 4 filters. So let's say we have 4 filters. And each of these will transmit 50% of natural radiation. Oops. It's supposed to be 50% of natural radiation. By that we mean unpolarized light. So it will transmit 50% of unpolarized light. So 4 filters. Filter number 1. It's going to be an isotropic filter. So it doesn't, it will pass all states equally. And we'll say it transmits I0. Okay? Filter number 1. Filter number 2. Filter number 2 is going to be a linear polarizer. At 45 degrees. Excuse me. It's a linear polarizer. Transmission axes are horizontal. Transmits I1. Okay. Filter number 3. I'll change color here. change pens. Another linear polarizer. This one transmits at 45 degrees. And the amount that it transmits, probably guess that, I2. Okay. Number 4, filter number 4 here, is we have a circular polarizer. Let's say it's opaque to the left-handed state. And it transmits I3. Okay. So these are our 4 filters. Isotropic filter, passing all states equally, transmitting I0. Linear polarizer, transmission axis horizontal, transmits I1. Linear polarizer at 45 degrees, transmits I2. And circular polarizer, opaque to left-handed state, transmits I3. Okay, now what we're going to do is, in terms of these I0, 1, 2, and 3, we're going to define Stokes parameters. And S0 will be equal to, defined as 2I0. We'll come back to that in a second. S1 will be defined as 2I1 minus 2I0. S2 is 2I2 minus 2I0. And S3 is 2I3 minus 2I0. Well, we said that each one of these filters transmitted 50% of natural radiation. We said that filter number 1 was an isotropic filter passing all states equally, and it transmitted I0. S0 is equal to 2 times I0, so this is equal to the incident irradiance. And so as we go through this, looking at the Stokes parameters, S0 is tell us how much light we had incident. These guys, S1, S2, and S3, are going to, as we'll see in a little bit, specify the state of polarization. Okay. So what we'll do now is kind of look at these and kind of see what they're saying about the polarization. And as we do that, we need to go back and look at the definitions of these filters. So I'll ask you, if S1 is greater than 0, what does that mean? Well, remember that S1 came from I1, which comes from a linear polarizer with a horizontal transmission axis. So if S1 is greater than 0, then this will what? Resemble horizontal polarization. Okay. In the same way, if S1 is less than 0, any guess what this will say? Well, vertical polarization in that case. Okay. If S1 is equal to 0. Well, it's not horizontal, it's not vertical. So we're saying that the beam shows no preferential orientation. And so it could be circular. It could be unpolarized. It could be, say, elliptical at plus or minus 45 degrees orientation. We don't know, but we just know that it shows no preferential orientation. Okay, if S2 is greater than 0, well, let's see, S2 was 2I2 minus 2I naught. I2 was a linear polarizer at 45 degrees. And so if this is greater than 0, then it must resemble P polarization at 45 degrees. Okay. If S2 is less than 0, resembles what? P at what? Minus 45 degrees. Yeah. If S2 is equal to 0, well, neither of the above. Okay. Now let's look at S3, and I have all these lights flashing up here. Race to the end here. If S3 is greater than 0, well, S3 was 2I3 minus 2I naught. Remember, I3 came from a circular polarizer, opaque to the left-handed state. And so if this is greater than 0, this is a tendency towards right-handed circular. And S3 less than 0, tendency towards left-handed. So we've gone through here looking at the 4 Stokes parameters, and we kind of have ideas as to what they mean. We will go through next class and calculate these Stokes parameters. We will go through and look at writing these in terms of vectors, and then we'll go to what we call the Mueller matrices to write the different optical components in terms of matrices and see how useful that might be. And then when we get through that, we'll go on to chapter 4 and begin talking about interference. So between now and next class, we have 2 basketball games, and you also have a homework assignment due next class. And so anyway, have a good weekend. We'll see you next week.